record. Okay. So under our camera, I'm going to go to page 34 in our book. So I'm going to zoom in here. This is our sample problem 2.3 that we're going to be looking at. And this problem wants us to look at the four forces that are on bolt A and determine the resultant, or the one force that is going to replace all four of these. Now, in this sample, or in this section, if you recall, the last time we were together, we looked at breaking forces into their X and Y components, okay? But it was only one force. We just broke the forces into the X and Y components, or had the components and then found the force that it was for. So what we're going to do here is we're going to use a process called rectangular component method for solving for the resultant of, in this case, four forces that are acting on this bolt. Now, this is what we would call, if you would, an analytical solution. We're going to draw it to represent what's going on graphically, but we're not going to solve it graphically. So we're not going to use the triangle method or the tip-to-toe method or the parallelogram method, okay? What we're going to use is what we would consider to be an analytical method, doing the math, if you would, to find the values, but we're specifically going to be using the rectangular components of the individual forces to find our answer, okay? So let's, like I said, jump into a sample problem 2.3 here, and we are going to walk through this process by doing a problem as we go. So I am going to start by drawing out the diagram that we have with point A at the center, and you're going to want to do the very same thing. Now, what I'm going to encourage you to do is to use about the top half of your paper to draw that diagram. Do not try to squeeze this into a small little area, because the expectation is, as you know, you're going to be putting labels on things, you're going to be putting arrowheads, and you have to be able to fit that all in, okay? So again, I am going to take literally the top half of my paper to draw my X and Y coordinates here. I'll zoom out even a little bit more so you can see the full thing. Okay, so this is going to be my X and Y axis, all right? And we are going to have our positive direction of X and Y to be in, like, if you would, the standard. So on every one of the problems going forward, okay, we are going to put up in the upper right-hand corner something we call the convention, okay? And the convention says anything going to the right in the horizontal direction and anything going up in the Y direction is going to be positive. If you do not add your convention, it's -1 on your problems, okay? And that's on every problem. We're going to use the same convention all the time, but it's important because later on when we identify our equations, the positives and negatives are going to be based on this, okay? So convention has to be in the upper right-hand corner, always, always, always. So then now what I'm going to do is I am going to draw each one of my forces. Now, I have a protractor, but I'm not going to figure out exactly the angle. I am just going to, by proportion, kind of draw in each one of the forces coming from the center. And I want to make them proportional. So for instance, the 150 newtons should be longer than the 80 newtons, okay? And going straight down. Now I'm going to draw my arrowheads on each one. Now, something I noticed when I've been getting some things in is that some forces that you're drawing for me don't have arrowheads. You're getting points off for that, okay? Every vector that you're showing has to have an arrowhead. Additionally, you have to label X and Y components on the X and Y axis. They are not floating. We are not floating anything, okay? So that's why they're called X and Y components. They fall on and they lie on the X and Y axes, respectively. So our first force is called F1, and that's going to be equal to 150 newtons. And then it is at a 30-degree angle. And then we have another one here. This is 15-degree angle. This is F4, and that's going to be equal to 100 newtons. And then I've got F3, equal to 110 newtons. Okay. And F2 is equal to 80 newtons. Okay. So each one is called out with their label. They're giving it to us in the example, so we want to follow along with that. Now, so the first step I'm going to say, okay, this is going to be your vector diagram. Okay, first step is always going to be the vector diagram. So you're just going to put, the forces that you know here. Step number 2 then in this process is going to be the components. Okay. Now we're only going to do X and Y components of any forces that don't directly lie on the X or Y axis. In this case, force 3 going down lies on the X and on the Y axis. So we are not going to calculate components for it. It's just going to be on the Y axis. But F1, F2, and F4 do not lie directly on the X or Y axis, so we need to find their components. So to do that, we have to draw the component where it's located, as well as label it. And that's why bigger, better, okay? So I'm gonna come down, I'm gonna use my F1 first, and I'm gonna offset from my axis just a little bit, because I can see I'm gonna have another one below it, so I'm just gonna offset just a little bit. It lies on the axis, but you can just see that it's just slightly offset. And this is gonna be F1X. Okay. Then I want to do that very same thing for the y-axis. Okay. So here too, I can see there's going to be another component on the other side here. So I'm going to offset this y component just slightly so that when the other one comes in, I can see the difference. And this is F1y. F1y is not out here. F1x is not up here. It's not on the dotted lines. They are on the X and Y axes. They have to be there. Yes, I am being picky about that. Points come off if you don't do that. And again, arrowheads, we are drawing vectors here. They have to have magnitude and direction. The only way I know which way that they're pointing is if I have an arrowhead on it. Points come off if there's not arrowheads on your vectors. Okay. All right. So I'm going to start with my F1, X, and Y. I'm going to calculate those components first, and then we'll kind of move around, okay? So since I've got these drawn here, yes, I can envision and I can see a right triangle here, right? I'll just highlight it here. So if we would, I've got a right triangle right here, okay? Yes, my F1Y is an equivalent length to the dotted line out here that's vertical, but it is not located there. So you're not putting F1Y. Nobody's putting F1Y over here, right? If you do, erase it now. No, don't hand it in like that. And don't be drawing that vector out here. We're not, again, we don't want any floaters. Okay. All right, but it's an equivalent length. So as we look here, you can see that we know the angle 30. And we would need to find what is the magnitude of F1X and F1Y. Let's start with F1X, okay? F1X is the side adjacent to the 30 degrees, and we know the magnitude of the hypotenuse here, right? F1. So which trig function, sine, cosine, or tangent, is going to help me find F1X? Cosine. Cosine, is it? Yes, absolutely. So if we go down here, step number 2 is our components. I'm going to say that F1X is equal to the cosine of 30 times 150 newtons, which is F1, right? It's the hypotenuse. So multiplying those two out, finding the decimal equivalent, 30 cosine, 150. So it looks like F1X is equal to 129.9, probably 130, but I'm going to hold an extra decimal place as we are working our problem here. I'm just going to put my little cloud around here just so that when I need it, I'm going to go back to it, but also add units here. This is a force. The units of force for this problem are newtons. So you are saying F1X is equal to 129.9 newtons. Don't end at 129.9 and magically let your units appear at the end. That's not how we operate. We're putting the units in all phases of the problem, including here and here, okay? Now, if you are solving for an F1X, I better see F1X up in your diagram here somewhere, clearly labeled, okay? If you don't have it labeled, points off. Okay. All right. Let's do the Y component. I tend to put all my X components on the left-hand side and then my Y components on the right-hand side. So I put this little divider in between. So I'm going to say F1Y. Okay. Now F1Y, if we look here, it's an equivalent length out here, right? We can imagine it out here, but it's not located there. But if I have my 30 degrees here and I look to F1Y, that would be the side opposite on this right triangle. And I have my hypotenuse. Which function would I use? I heard the sine. Yes, that's exactly what we're going to use. So this is going to be sine of 30 degrees times our hypotenuse, which is 150 newtons. Include the newtons in all phases of the problem. So you put newtons in back of the 150 here. So now you're going to multiply that out. My F1Y, what do we get for that value? Yep, 75. Because the sine of 30 is a half, right? But it's always good to check it on your calculator. So 75 newtons. And we're going to put our little cloud around that too. Again, you don't have to put the cloud around it, but don't put a box around it. Remember, boxes are reserved for final answers only. That'll be our resultant, magnitude, and its angle. Okay. Let's go to our next one. Let's go up to F2 here, which is 100 or his 80 newtons. I forgot to put my 20 degrees in here. Now, here's a choice that you get to make. All right. Many times when we're doing X and Y components, we're going to have the angle given to us where, like we saw over here, where the cosine of that angle is going to give us the X component, and then the sine is going to be the Y. But in the case here, if we look and we put our X and Y components in place, we're going to notice that it's actually just the opposite. Okay. So be careful of the placement. So we could either use 20 degrees where it's at right now, or we can use the 70 degrees if you like doing the cosines for the X's and the sines for the Y's. But then we're going to have to use 70 in that case. So this is going to be F2X. And then up here, see, this is where it gets like squishy. Even mine, I'm pretty big here. And mine is I'm going to have to like, whoop. F2Y is going to be that one right there. Could never be too big. I could have made mine bigger. So I'm going to use the given information. So in this case, I'm going to use the 20 degrees. But like I said, you could use the 70. You could use the 70 and use the cosine for the X and the sine for the Y. But I'm going to use the 20. So that means that when I look here, my 20 degrees, my Y component is adjacent. Okay, so I'm going to highlight this little triangle here. Okay, my Y component is adjacent. So my F2Y, so I'm going to go on the right-hand side here. My F2Y is going to be equal to the cosine of 20 or the sine of 70, up to you. Either one works, times 80 newtons, which is the hypotenuse of F2. So F2Y then, what do we get for our value? Yeah, I'm going to put 0.18, and that's going to be newtons. So make sure you add your newtons there. Okay. And for those who are virtual, feel free. I'm going to pull the chat out, and you can always add the answer in there if you want to contribute. All right, now we've got to do the X component. The X component on our diagram is right here. Okay. But we know that if we look at our little highlighted triangle here, it would be equivalent to the opposite side of the 20 degrees. So that one is going to be our sine of 20. So F2X is going to be equal to the sine of 20 or the cosine of 70 times 80 newtons. Okay. But something that I want to emphasize is on some of these problems, you're going to get one of those little angles in there. So don't assume every angle you're given, the cosine is the X and the sine is the Y. Make sure that you look where it's located, because in this case, it is opposite. So what do we get for F2X? 27.36 newtons, right? Anybody else get that same number? I don't have it in front of me. Well, I do. Second. Yeah. Cool. All right. Now we have one more. I'm going to let you do this very same thing for F4, and then we can compare the answer. So I'll do it alongside here, and I'll do my work down below. You go ahead and you do it as well. And then we can compare. So as you're getting your answer for FX and FY, I got 96.59 for FX, for F4X, and then for F4Y, 25.88. Okay. All right. Any questions so far? All right. Now, what we've done here, we have broken 4 forces. We now have how many? 7 forces, right? We broke F1 into X and Y. We broke F2 into X and Y, so that's 4. 6, because we've got F4, and then we've got 7 with F3 going down. Now, why would we do that? Any idea what maybe our next step is going to be? Okay, you say you're going to add them all up. We're going to add them all up, but why? So you'll notice we brought them to the X and Y axes, right? So we only have forces now horizontally and vertically, right? And I think that's where you were going with that. What that offers us is when we have forces, as we know, or maybe you don't know, when they act along the same line of action, we can add them algebraically. Okay, so that means that anything on the y-axis, if it's going up or down on that y-axis, we're going to assign a sign to it. If it's going up, we're going to say, oh, that's in the positive direction. If it's going down, that's going to be a negative direction. And now we can add and subtract the verticals. And then we can do the very same thing for the horizontals. So what we've done is we brought those forces onto common lines of action. Okay. Before, when they're going in all different directions, we don't have that, right? So that's what components do for us. Yes, we're dealing with more forces, but they're now on a common line of action for each direction. Okay, so the next thing that we're going to do now is we're going to look at each one of these directions. Okay, so I'm going to go to my next page here. Step number 3. Okay, step number 3 is going to be summing our forces along the x-axis. Okay, so this symbol that I'm using right here, this is capital Greek letter sigma. Okay, that means we're going to sum. That's the summation symbol. Okay, the forces, capital F, in the x direction, so sub x. You have to write it just like this. You're not going to leave it f of x. No. We're going to sum the forces. That's what that symbol does. So you have to show that symbol in front. Sum the forces in the x direction. That is going to be equal to our resultant X component. So what we're trying to do here is we're trying to find out for our final resultant, what is the net effect in the X direction? Okay, and that's what we're going to do with the sum of the forces in the X. So to do that, we're going to go back to our diagram here. And we're only going to look at what's happening on that horizontal or that X-axis. And we're going to give each one of those values a sign based on our convention. So I'm going to start with F2X. I'm just going to work left to right. I have F2X here. So I'm going to start that off. I'm going to put a minus sign in front of that. F2X, minus F2X. Why is the minus there? Because it's pointing to the left. That's why we need an arrowhead. If you do not put an arrowhead on something, you can't say which way it's going. I can't give it a sign. Okay? Very important. Now I'm going to look. I've got an F4X going to the right. I'm going to add that in. So that's going to be a plus F4X because it's going to the right. And then I'm going to have a plus F1X because it is also going to the right. Okay. Now, once I've exhausted all forces on the X-axis, which I have, and this is why, if you'll notice here, you see that little bit of a separation on the X-axis? I can see that there's two forces there. If I don't do that, sometimes if you go over the top, it's easy to miss. So it's just kind of a suggestion to make sure that you can definitively see that there's two forces, you know, if they're acting on the same axis. Okay. Only those, right? So now if I have all of those exhausted, I'm going to set that equal to Rx because I did the left-hand side of my equation is summing the forces in the X direction. And then it's saying, oh, those are all going to be equal to Rx. Now I'm going to put my values in place. So I'm going to look back down at our bottom here, and I'm going to add in the appropriate values. So I'm going to have a negative 96.59 newtons because we're putting our units in all phases of the problem. Oh, I did that wrong. I'm so sorry. F2X is the second one, negative 27.36. Sorry about that. Plus now 96.59 newtons plus 129.9 newtons. Okay. Newton, Newton, Newton. We're putting the units and back of each one of these values. Remember, they are vectors, so they have a magnitude, but they also have units, okay? And we're working in the metric system, so it's newtons. And we're going to say equal to Rx. Now I can just simply add and subtract this and get my value for the resultant X component. What'd you get? 199.4. And that's in the book too. So 199.44.
Book had 199.1, but they rounded way up.
Right, and we carried extra, so it was 44. They always, and this is the caution when you're following along in the book, or even for final answers, you'll notice yours are probably different. What I want you to do is I want you to hold 4 and 5 decimal places, or when we're working with newtons, we have, we're holding extra, but they're rounding to 3 significant on every single one. Okay. And so sometimes you can get a different answer. Brooke, do you have a question?
That's the 199.
Did you? Okay. Oh, you did. Jacob. Heck. All right. So it's 1-3.
Yeah.
Okay. Just double check, Jacob, to make sure. I'm not always doing it along with you guys either. Okay. Now, notice here that we ended up with a positive value. Okay. Positive value. That gives us direction as well, because as per our convention, we know that positive values are pointing to the right. So this tells us that the resultant X component is going to point to the right. All right. So pay attention to these signs. It's very important. But before we worry about drawing it out, we are now going to sum our forces in the Y direction equal to the resultant Y component. Right. Now we're going to go back to our diagram. We're going to look vertically. Okay. We've got a positive F1Y and a positive F2Y. Right, so I'm going to write those first. Positive F1Y, positive F2Y. Then as we look down, I've got two forces. Don't forget the 110. Okay, remember that didn't have a component, but it is an actual force going down. So we have an F1Y, and then we have 110. These are going down, so it's going to be 4Y, and then minus 110 newtons. And then that, because we have that value right away, is equal to the resultant Y component. And now we want to fill in the values for each one of those Y components. So I've got 75 newtons plus 75.18 newtons minus 25.88 newtons minus 110 newtons to RY. And I got exactly the 14.3. Let's get that same thing. Okay. And notice also its sign is positive. So that means that, again, according to our convention that we did in our upper right-hand corner here, it's going up, right? So now what we've done is we've taken 7 forces and we reduced it down to 2. Okay. These are their equivalents along the X and Y axis. So our step number 4 now, okay, is going to be calculating the resultant. Okay. Finding its magnitude and its direction. Now, you will draw your X and Y components. So this is where we're going to be looking at, all right, here's our RX. That means that this is going to be going along the X-axis to the right, pointing to the right. And it's going to have a magnitude of 199.13 newtons. Then in the Y direction, pointing up, we're going to have another vector, 14.3 newtons. This one, the X is going to be much longer than the Y, but you are going to draw this, and this would be drawn in the first quadrant because both of our forces are positive. So you are going to draw kind of a short, probably a short little Y-axis and a pretty long X-axis. You don't have to scale this, but proportionally, you want to show the resultant Rx along that X-axis, okay? You wanted to show it considerably longer and pointing to the right and labeling it Rx is equal to 199.13. And newtons is its units. And then a short little RY. This is Y, this is X. And that is 14.3 newtons. Okay. You have to draw this diagram. This lets me know that you understand what you just calculated means. Okay. And putting the arrowheads on and the directions is really important. Okay. And again, if I would have a negative value for either one of those, then I would be drawing it in the opposite direction. Okay. All right. Once I have my X and Y components, then I'm simply going to draw in my construction line parallel to either one of the opposite forces through the endpoints of each one of those. So I'm going to kind of draw this rectangle. Through the endpoint of Y, I'm going to draw the line parallel to the force X and parallel to the Y through there. And then starting at the origin, I'm going to draw a line. My tail of my resultant is going to point to, or the tail is going to start at the origin and the tip is going to point to that intersection that I just created. Now, again, if you're pretty good at drawing lines horizontally and such, that's totally fine to freehand it. But if you know that you are challenged with that, then a straight edge is good. Then you're going to label this. This is the overall resultant. So it's just going to be called R. Okay. Now remember, magnitude and direction. Direction is identified on a vector in 2 ways, arrowhead and the force, or I'm sorry, the angle, the angle. So we need to add in here an angle. Most often, we're always going to go from the horizontal axis, and we're going to call this theta. That's going to be the kind of my default most often. Letters like theta, alpha, phi, those are angle designations, if you would, that are popular with Greek alphabet, but theta is probably the most popular. So I'll usually default to theta. All right, so we need to find out the magnitude of our R and its direction. So starting with magnitude, any ideas how we could find out how long our resultant is? What is the magnitude? Pythagorean theorem, absolutely. So the R is our hypotenuse. And then we've got this, just like we did before, we've got that right triangle. Now we this time know the components. So we know the legs, if you would, of the triangle. We know the side opposite here, or I guess normally in that standard form, it would be c squared is equal to a squared plus b squared, right? So we know the a and the b, we know the legs, and we want to find the c. So in this case, we're going to have r is equal to the square root of our x squared plus our y squared, okay? And then you're going to put your numbers in place. So our x under the radical, 199.13 newtons, and we're going to square that entire quantity, plus 14.3 newtons. Put your units in all phases of the problem. We're going to add those two together, and we're going to take the square root. What do we get for the magnitude of our resultant? You get something like 199.6-ish? 0.64. Okay, thank you. 199.64 newtons. We square the newtons under the radical, but when we take the square root, they get back to newtons. So I don't want to see any magically appearing newtons. This is not Lucky Charms. Brooke.
So it's the magnitude or?
Oh, do you mean the absolute value? No. What we're going to do is this is one of our final answers, so we will put a box around. Is that what you're asking?
No, I mean, you have to show that, like, put the two absolute value.
No, you don't. Okay. So that's our magnitude, but now we need to know direction. So we need to calculate what our theta is going to be. All right. So what is the angle that this makes to horizontal? Now, another point I'm going to make here is notice that I labeled it R here and I solved for it here. If you're putting a box around something that is R is equal to, I'm looking for R up in your diagram. In this case, if we're going to be solving for theta is equal to, then I better see where theta is up in your diagram. Okay. All right. So here's theta. And I know the legs of my right triangle. I also know my hypotenuse. Now, all of our values here are calculated, all right? And the least calculated technically are the two legs. So I'm going to use the two legs. You're going to see most often we use the tangent function using those two legs. So just going to kind of make myself a little sidebar here. So I'm going to say tan theta is going to be equal to, it would be the side opposite, which would be my ry. Ry is not out here. It's on the y-axis. Ry divided by, Rx. Divided by the side adjacent. So that means that our tan theta is going to be equal to 14.3 newtons divided by 199.13 newtons. Newtons cancel out here, and we'll get a decimal. And then we can take the inverse tan function. And I'm getting 4.11 degrees. They got 4.1. You need to draw your final diagram here showing those X and Y resultant components so that you can calculate the resultant. And then magnitude and direction. Boxes go around these two because this is my final answer. The problem was determine the resultant of the forces on the bolt. The resultant is 199.64 newtons going up and to the right at 4.11 degrees. And that will replace those four separate forces. So if we go back to kind of the original illustration right here, these can be replaced with this one force and have the same net effect on the body. Okay. All right, now let's review the steps here that you have to go through for problems like this, okay? First things first, you draw your diagram and then you put your components in place. Top half, top third of your sheet, okay? Make yourself a lot of room so you can see all the labels. I don't want it little tiny. Make sure you have your convention at the top of each one of these problems. Then the second step is going to be breaking any forces that do not lie directly on the X and Y axis into their X and Y components. Okay. Step number 3, summing those forces along the X, along the Y to find the resultant X and the resultant Y components. Their sign tells you the direction. Both of these are positive. They both went to the right and up, so they were both positive according to our convention. But if you would end up with a negative value, then that dictates the way that that vector is going to point. And then the last step is to take those components, draw them on a diagram. You have to draw this for me, okay? With all the labels, and then solving for the magnitude and direction of the resultant. Box around those. Okay, so it's a little bit of a process, and there's you know, stuff that you have to write out. So so you're going to see that there's going to be some problems that you're going to solve using the rectangular component method. That's what this is called, the rectangular component method. All right. Okay. So I'm going to, at the moment, stop our recording here because I think it's good to have like one problem, and then that way you can go back to this one. I'll have it labeled.